Hi guys. In the last lecture, we were discussing the the classification of magnetic materials. So basically, we have seen till now two kind of materials. The first one is the diamagnetic material, where once you apply the external magnetic field, the material repels or excludes the magnetic flux, and there's something called perfect diamagnetic material, which is a superconductor because it expels all the magnetic field inside it and throws it outside. You see this figure, the yellow part, if that's a superconductor. Okay, and then we saw the second category, which is paramagnetic material. And in paramagnetic material, actually, there is an unpaired electron, and this lead to a net magnetic moment for an atom or ion. Okay, for the entire system, one can think of the net magnetization would be zero, because there are so many different atoms or ions, and they will be oriented in all different directions, but individually they have the magnetic moment. We also introduce, let's say, the Curie temperature, below which that's the transition point from ferromagnetic to paramagnetic phase. So today we'll have three more materials: antiferromagnetic, ferromagnetic, and ferrimagnetic. So I'll discuss the antiferromagnetic material. So in antiferromagnetic material, as in the last to last lecture also, I told you that spins are oriented in this fashion: one is up, one is down, if let's say the system is in one dimension. Similarly, you can extend it to 2D or 3D. So the individual atom or spin has a net magnetic moment. However, these magnetic moments, they are aligned in an anti-parallel way. Okay, so I'll just start it down. So individual atom or ion has a net spin moment, magnetic moment. However, the magnetic moment are aligned in an anti-parallel way. There should be just 1 hour. Okay, so that's the antiferromagnetic materials for us. The example of antiferromagnetic material system, you can think of chromium or alpha manganese, the antiferromagnetic elements, I can say, chromium or alpha manganese. And compound, if you want, manganese oxide is one of the example for antiferromagnetic material. So for these antiferromagnetic material, the susceptibility is slightly larger than 0, but it depends on the applied field intensity. Okay, and okay, so chi m, the susceptibility, is slightly larger than 0. So if we heat an antiferromagnetic material, so eventually what happens, all the antiferromagnetic coupling, it will be destroyed. So antiferromagnetic coupling meaning this arrangement of anti-parallel way. Okay, the spins are arranged in an anti-parallel way. That's what is called antiferromagnetic coupling. So if we increase the temperature, of course, because of the thermal energy that you are imparting the system, so the coupling gets destroyed and the material becomes paramagnetic. The spins are oriented in all different directions. All right. So again, there is a transition from antiferromagnetic to paramagnetic phase, and this transition temperature, it's called the Néel temperature. All right, so I'll just write it down whatever I say, but if we heat an antiferromagnetic, okay, I'm not writing it down completely, just you can understand antiferromagnetic material. So the coupling gets destroyed and the material becomes paramagnetic. Okay, and the transition, the temperature at which this phase transition appears happens, it's called the Néel temperature. It's similar to the Curie temperature, which is from paramagnetic to ferromagnetic. And the Néel temperature, it's denoted as Tn, or sometimes people also denote it using theta n. All right, so above Néel temperature, we have paramagnetic phase in the system, and below Néel we have antiferromagnetic system. Okay, so now I'll combine the ferromagnetic and ferrimagnetic phase because the properties are more or less same. Magnetic materials. So what happens in these material? These materials have the strongest response to externally applied magnetic field compared to all the categories that you have seen till now. So in other words, you can think of that these materials are way more susceptible to magnetic field than any of the other materials. So I think we have discussed it. In ferromagnetic material, actually what happens, the most important feature is there is a net magnetization even without magnetizing field. Okay, and why this happens? It's because of the spontaneous alignment of the magnetic moment in the solid. Okay, that's the main difference between that's the characteristic feature of ferromagnetic or ferrimagnetic. And if you remember, ferromagnetic, I was saying that all the spins are pointing in the same direction. And ferrimagnetic, so this is ferro. And what happened in ferrimagnetic? So in ferri, there was, let's say, up spin, but the down spin moment was smaller. So the overall, the net spin moment would be in one direction. So ferri is kind of ferrimagnetic has the properties of both. It's ferromagnetic in the sense that it has a net magnetization even without magnetizing field, and it has a property of antiferromagnetic in the sense that the spins are aligned in an antiparallel way. Okay. All right, so that's ferro and ferri, and the most important feature, as I said, the important feature, there is a net magnetization. Even without the magnetizing field. and this is due to the spontaneous alignment of magnetic moment. Okay, and if we have spontaneous magnetization, the one thing that comes in mind is the hysteresis loop also. Similar that we had, you remember, in the ferroelectric material. So in between polarization and electric field, we could define hysteresis loop. Similarly, for ferromagnetic or ferrimagnetic material, we have hysteresis loop. But I want to, before telling you about the hysteresis loop, actually I want to just give you the same way that we had the Curie-Weiss law in the ferroelectric case. The similar thing we have here also. So when we go beyond a temperature, which we can denote using Tc, we denoted earlier, so let's denote it as via theta something, theta c or theta p. So above this Curie temperature, your system becomes paramagnetic, and below it's ferromagnetic or ferrimagnetic. Then the susceptibility, it's inversely proportional to the temperature, or I can just write it down what the Curie-Weiss law tells us. So it says, it describes the variation of magnetic susceptibility, which will be chi m. So I can write it down, chi m is equal to C divided by T minus theta p. So that's the Curie-Weiss law, the variation of chi m with temperature. Okay, and theta p is the Curie temperature, and C is the Curie constant. Okay, so exactly same like the previous case. I also like to introduce okay, no, first let me discuss the hysteresis loop, then I'll discuss something called the easy axis, and such that whenever you see these kind of terminology, you know which direction we are talking about. Okay, so let's now discuss. We have already seen in great detail the hysteresis loop for dielectric material. Okay, so the next topic will be the hysteresis loop for ferromagnetic and ferrimagnetic materials. Actually, it's similar like the dielectric material which we saw, but this time it's in between the B and H. So B is like your flux density, inductance, or and H is the magnetizing field. Okay, so like we did last time, we start from zero magnetizing field. So you start from the origin, and in the beginning it's linear, the curve, but as you increase the magnetic field, you see the nonlinear behavior. So let's say we reach a saturation point A. Now once you start reducing the magnetic field, instead of coming back to the origin, the let's say this point is B. So when the magnetizing field is 0, so the flux density or the inductance doesn't become 0. So this thing is called retentivity. Okay. So even though the magnetizing force is 0, there are some inside the ferromagnetic or ferrimagnetic material, the system has not completely, the spins have not completely aligned to align in some random direction. They are still pointing in one axis. Okay, so now to get rid of this magnetization in the system, we need to apply a magnetic field in the reverse direction. So let's say we reach a point C here, and this is called coercivity or coercive force. Coercive field, you can say. We are talking about the H. So it's coercivity, this process. Now one can do the similar thing in the negative H direction. So you go to a saturation, like the A point will reach a D point, a saturation, but it's in opposite direction. Then once we come back, instead of going to 0, we reach a point E. So this is again retentivity, but it is in opposite direction, okay, because field is applied in the minus whatever direction you applied the previous one. Okay, so now if you go, if you follow a bit more, you decrease the magnetic field. No, sorry, now you increase the magnetic field because already the magnetizing field has reached 0, but to have 0 inductance in the system, we need more magnetic field. So you reach a point, let's say F here. All right, so and further we go from F to A. Okay, so here A is the saturation point, D is the saturation in opposite direction. So this is basically the hysteresis loop, and we also call it BH loop. And the hysteresis loop is basically really important from the practical aspect because it decides, depending upon what kind of system we want to make. So whether we should have a large coercive force kind of loop or small coercive force kind of loop. So what do I mean by that? Meaning, see, I can have a hysteresis loop which is pretty abruptly changing. Okay, so let me do it properly. So let's say it's something like this. Okay, and I can have, let's say this is one case. I can have another condition where it's broad. The area of the hysteresis loop is pretty large. Not that much pretty, but it's okay. Okay, so if the coercive force, the coercivity is low, then this is called the soft magnetic material. And if the area of the hysteresis loop is pretty large, so this is called the hard magnetic material. Now, depending upon the use, meaning, for example, if you want to have, if you want to use it where the magnetization direction we want to flip it frequently. So we need this area has to be smaller, right, such that you can flip the direction of magnetization easily. So for example, transformers or generators, uh, you require a material, or you need to build a material which has a small hysteresis loop area. But if you want to use, let's say, if you want to store data, okay, if you want to use it for information storage, we would like to have a large coercive field, meaning you need to apply a magnetizing field in opposite direction, which has to be pretty large, such that the it's stored, the whatever memory it had, it's completely lost. So that's why, depending upon the application, one need to choose whether we want a soft magnetic material or a hard magnetic material, and what will tell us that thing? It will be the hysteresis loop, which will tell us. Okay, apart from this, I also want to tell you about the easy access and hard access. So this is also one definition which people use pretty often in the magnetic material. So easy access is the direction in a crystal, okay, along which if you apply a small magnetic field, it's sufficient to reach the saturation magnetization, meaning this point. Okay, I forgot to draw this line. Let me draw it. Okay, so easy access, it's the direction inside the crystal. It's the axis along which a small magnetic field gives saturation magnetization. Okay. So there is another thing which is called the hard axis. So it's the axis or one particular direction inside the crystal, along which you need to apply a large magnetic field along this large magnetic field to reach saturation. Okay, so this is also a pretty common word terminology which people use in the magnetic material, but you just need to know that easy access means it's easy to if you apply small magnetic field, it's easy to get the saturation magnetization along that particular direction. Okay, and hard axis would be, for example, let's say if your spins are more or less aligned, or they are along the z-axis. So if you apply a magnetic field along z-axis, so you will reach the saturation magnetization very quickly, right? Because most of the spins are oriented along the z-axis. However, if let's say you apply your magnetizing field along x-axis, so you need pretty large magnetic field along x-axis such that all the spins align towards the x-axis. So that's what I mean by the easy axis or the hard axis. Okay, so this was another set of definitions, and we also saw the practical aspects of the hysteresis loop. Now I want you to tell, I just want you to tell there's something called magnetic anisotropy also. And as I said, that the magnetic anisotropy means the magnetic properties, they are dependent on the crystallographic direction, meaning whether it's easy axis or hard axis. So your crystallography direction is going to define the magnetic properties of the system. Okay, so let's begin with the I just want you to introduce this concept. We are not going to derive or understand it deeply. So it's magnetic anisotropy. Okay, so I can just write down what's magnetic anisotropy means. It means that the magnetic properties are dependent on the crystallographic directions. Okay, direction. So that's what magnetic anisotropy literally mean. So this is really critical if you want to have a permanent or a hard magnetic material. So how? Because let's say a coercivity or a coercive field of a magnetic material is related to the magnetic anisotropy in two ways. So one is called the magnetocrystalline anisotropy. So magnetocrystalline anisotropy. So what happens in magnetocrystalline anisotropy? It means that if I give you a crystal, the magnetic property, they will change if you, depending upon the crystallographic direction, meaning if you are along 100 or 111 or 110 plane, the effect, the hysteresis loop, it's going to be different. The area, the amount of the coercive field you require, it's going to be different. So this is called the magnetocrystalline anisotropy. Okay, and there is a really common terminology that we use. So the energy need to rotate from easy axis is known as magnetocrystalline anisotropy energy. Why I'm telling you? Because in the next section, when we'll discuss the domain walls, this anisotropy energy plays really crucial role. Okay, so just understand, in the magnetocrystalline anisotropy case, the energy needed to rotate from the easy axis, and when I say easy axis, it means easy magnetization direction, right, where we apply small magnetizing field, and you get the saturation magnetization pretty easily. Okay, so easy axis is known as magnetocrystalline anisotropy energy. All right, so meaning that if this energy is large, that means that you need the interaction between the two neighboring spins would be pretty high, because that means that you require more energy to rotate from the easy axis. So you need to put more magnetizing field in the system. You need to apply more magnetizing field in the system if you want to rotate this spin from whichever direction to its easy axis direction. Okay, so this was the first way. The second way is something called magnetoshape anisotropy, or I can just say shape anisotropy. So it's magnetoshape. So what happens in magnetoshape anisotropy? So depending upon whether the material is, let's say, needle-like or sphere-like, you have different coercivity in the system. So depending upon the shape of the material, the coercivity changes. And you know why we are focusing on coercivity, right? Because this decides whether we want to have a soft magnetic material or a hard magnetic material. I mean, depending upon the application, of course. Okay, so this is the magnetic anisotropy. Now, the last part of this course, it's the magnetic domain walls. We have seen the domain in the ferroelectric case also. It's the same thing. So inside the, let's say this is our material, we can have different patches in the system which will be where the spin will be pointing in one particular direction. So that is called the domain, magnetic domain, a small group of atoms. Uh, they are, let's say it's something like this. Instead of saying, I can just draw, meaning here it's like this. Okay, so these are called the domains. So where the spins are pointing along one particular direction, and these lines, they are called the domain walls or the boundaries. All right, now as I said, this anisotropy energy plays really crucial role in deciding whether we are going to have what kind of domain walls we are going to have. So for example, if you want to zoom in this domain walls, what happens? Let's say if I want to go from up spin to down spin, so what happens? It will be, let's say, up, up, and then gradually it will start tilting. Then it will become like this. Okay, so this region from here till here, this is the domain wall. So let's say, okay, let me use different color. This is one domain, and this is another domain. Okay, and this is our domain wall. All right, so now the width of this domain wall depends on two factors. Two factors are the deciding ones. So what are those two factors? So those are called, let's say the first one is called the anisotropy energy, which we just saw, and the second one is called the exchange energy or exchange interaction. So the, I'll just write it down, so anisotropy energy or anisotropy interaction, and the second one is the exchange interaction or exchange energy. So as I said, what anisotropy energy is, see, sorry, here, the energy needed to rotate from the easy axis direction. Okay, so the anisotropy energy, it kind of tries to rotate a spin, let's say from here to here. All right, so let's call it E1, and exchange energy is E2. So what is exchange energy? Exchange energy wants two neighboring spins to align along the same direction. All right. So if our E1 will be so we can have two scenarios: E1 is greater than E2 or E1 is smaller than E2. Anisotropy energy is large compared to the exchange, or it's small compared to the exchange. Then the domain walls, it will be thinner. Why? Because material will prefer to undergo magnetization in the easy direction. So the domain wall will be thin. Okay, because E1 is greater than E2. The exchange energy, meaning it wants to rotate itself along the easy axis direction. But when E1 is smaller than E2, that means that these spin want to stay, the nearest neighbor want to stay in the same direction. So the domain wall would be thicker. Okay, so that's why when I was explaining the anisotropy energy, I told you that we are going to use it later in the domain wall section. Apart from that, these are the two important factors. There are other factors as well, which I'm not going into the detail, the demagnetization part and all. But these two are also the really deciding ones if we ignore the other ones. And we can have two kind of walls basically. One is called the block wall, and the other one is called the Neal wall. So what happens? Let's say we had a thin material. So let's say in this patch, the spin was pointing along this direction, okay, and this side is pointing along this direction. But along this patch, the domain wall, the spin is out of the plane, meaning the spin is something like this. Or I can say, I can denote it like this, right? The magnetic field coming out of the plane. So this is called the block wall. Okay, we can have another scenario where, let's say, the same system, this side up, this side down. And now the spins, they are oriented in this plane itself. So this is called the Neal wall. Okay, so this I can say that coming out of this spin, this is going inside. Similarly here I can say this. Okay, this is for this spin here. Okay, so depending upon how these spins are pointing with respect to the plane where the initial the domains were there, I mean relative to the directions of the domain, that's gonna tell us whether it's gonna be a block wall or it's gonna be a Neal kind of wall. There is another way of uh, uh, defining the domain walls. So this is for, let's say, for magnetic thin films. For example, I can have 180 or non-180 domain walls. So 180 domain wall meaning we have some system, the similar system, let's say, and exactly the either the spins are pointing exactly at an angle pi from one another across the domain walls. So this is called the 180-degree domain wall. Similarly, we can have something like this way, this way. This is 90-degree domain wall. All right. So depending upon the relative angle between the different domains, that particular name will be given to the domain wall between them. Okay. So I think we are more or less done in this chapter and in this lecture also. So we have seen plenty of things. We compare the dielectric and the magnetic material. The important aspect of the hysteresis loop, the different kind of magnetic materials we saw: diamagnetic, paramagnetic, ferro, ferri, and antiferro. And based on the application, we can have soft magnetic material, hard magnetic material, easy access, hard access, and the anisotropy energy and exchange energy. These are the two which decides whether we are going to have thin domain wall or thick domain walls. All right, so this is it from me, and we are done with the magnetic materials, as well as with this I finish all my lecture.